Picture this, our Earth, a super hot ball with a molten outer layer known as magma. Now, you might be wondering, what exactly is magma? Well, let's take a moment to dive into that. Magma is a mixture of molten or semi-molten rock, along with some gases and other volatile elements. It is found beneath the surface of the Earth, and occasionally, it comes to the surface through cracks or during volcanic eruptions. Now imagine our early Earth, a sizzling orb of radiant red and glowing orange, spinning in the vast expanse of space. It's hard to believe that the cool blue planet we call home was once a blistering ball of magma, isn't it? But that's exactly what it was, over 4 billion years ago. Our Earth was born from the dust and gas left over after the formation of the Sun. Over time, gravity pulled these particles together to form a spinning disk of rocks and dust. As these particles collided and stuck together, they formed a hot, young planet. The heat generated by these collisions, along with heat from the decay of radioactive elements, caused this young planet to melt, giving rise to a sea of magma. But here's the thing about our universe. It's a place of constant change. Nothing stays the same forever, not even a molten planet. As the eons passed, the outer layer of this hot magma-filled Earth began to cool down, and as it cooled, it started to solidify. So there you have it, the early chapters of our Earth's incredible story. A tale that begins with a fiery sphere of molten rock spinning and glowing in the vast, dark cosmos. A story of formation, transformation, and constant change. A narrative that's still being written even as we speak. And we, my friends, are a part of this grand narrative. That was our Earth, a fiery sphere of red and orange goo. As the clock of time ticked on, the outer layer of this hot ball started to cool. Now you might be wondering, why did it start to cool? Well, it's like when you pour a steaming hot cup of cocoa. It's too hot to drink at first, right? But if you leave it sitting for a bit, it starts to cool down. The same thing happened with Earth. Over billions of years, our planet began to lose some of its initial heat. This heat escaped from the molten magma to the coldness of space. Yes, space is incredibly cold. And this contrast between the hot Earth and the cold space caused the outer layer of the Earth to start cooling down. But what happens when something hot cools down? It solidifies. Think about when you make jelly. You start with a hot liquid that you then put in the fridge to cool. After a while, it becomes solid. The Earth's outer layer underwent a similar transformation. As it cooled, the magma started to turn from a liquid state into a solid state. Imagine a bowl of tomato soup. When it's hot, it's all liquidy and swirlable. But if you were to cool it down, a skin might start to form on the top, right? That's kind of like what happened to our Earth. As the cooling process continued, a thin, solid shell began to form on the outer layer of the Earth. This shell was like a protective blanket, insulating the Earth and keeping the remaining heat inside. But remember, this was not a quick process. It took billions of years for this shell to form, and even then, it was not a perfect solid shell. It was thin and brittle, much like the thin ice that forms over a lake in the early winter. What was this shell made of, you ask? Well, it was composed of the first rocks of the Earth, the first solid ground that would eventually form the surface of our planet. But that's a story for another time. For now, let's just remember this. So a thin shell began to form around our Earth. But Earth wasn't content just to sit and spin. It had more in store. The planet was a restless child, spinning away on its axis, creating day and night, seasons and years. It was also moving in space, making its way around the sun. All this movement was not without consequence. You see, the newly formed shell that was Earth's surface was not as sturdy as it appeared. It was thin, brittle, and resting atop a sea of molten magma. Now imagine a potter's wheel spinning, the clay drying and cracking under the heat and the spin. Earth was no different. As it spun and moved, the solid shell began to show signs of stress. It started to crack, much like the mud cracks when it dries. These weren't tiny hairline fractures, mind you. These were massive, deep cracks that tore through the shell, creating rifts and ridges, valleys and peaks. The surface was no longer a smooth, unbroken sphere. It was a mosaic of cracked pieces. The Earth was literally breaking apart, its surface tearing under the strain of its own movement. But why did the shell crack, you ask? Well, it's simple physics. When a solid object like our Earth's crust is subjected to forces, it can only take so much before it gives way. These forces could be due to Earth's spin, or even the movement of magma underneath. The solid crust, thin and brittle as it was, couldn't withstand these forces. So it did what any object under stress does. It broke, forming cracks. These cracks were not a sign of destruction, though. Instead, they were the start of a new chapter in Earth's story. They were the precursors to the formation of something we now know as tectonic plates, but that's a tale for another scene. And so, the solid shell began to crack. It was a dramatic transformation, a testament to Earth's ever-changing nature. But remember, this was just the beginning. The real adventure was yet to come. These cracks didn't just make patterns on the surface, they did something much more remarkable. Imagine, if you will, the Earth's solid shell, covered in a network of cracks. Like a hard-boiled egg that's taken a tumble, the shell was divided into sections by these cracks. But these weren't just any ordinary sections. They were massive, irregularly shaped pieces of solid rock, each unique, each with its own boundaries defined by the cracks. Now here's where things get even more interesting. Each of these pieces, these giant chunks of the Earth's shell, became what we know today as tectonic plates. Yes, those same tectonic plates that we've been talking about. The ones that float on the magma, that shift and slide, that cause earthquakes and volcanoes. These plates were born from the cracks in the Earth's cooling shell. But how big are these plates exactly? Well, let's put it this way. Each tectonic plate is enormous. Some plates are so large that they contain an entire continent, and some even more. The Pacific plate, for example, is so big that it's actually larger than the entire continent of Asia. These plates aren't uniform in size or shape either. Some are relatively small, like the Juan de Fuca plate off the western coast of North America. Others, like the aforementioned Pacific plate, are incredibly large. But regardless of their size, each tectonic plate plays a crucial role in shaping our world. Now you might be wondering, how did these plates form from the cracks? Well, remember how the Earth's shell cracked as it cooled? As it hardened, the shell became brittle, and the motion of the spinning Earth caused it to fracture. These fractures, these cracks, are what divided the shell into these giant pieces, or plates. And it's not like the Earth cracked once and that was it. No, the fracturing was a process that took millions and millions of years. The Earth cooled, the shell cracked, pieces formed, and then those pieces cracked further, forming even more pieces. It was a cycle, a slow, continuous process of cooling, cracking, and forming plates. But here's the kicker, this process isn't done. Even today, new plates are being formed and old ones are being reshaped as the Earth continues to cool and crack. It's an ongoing, never-ending cycle, a testament to the ever-changing nature of our planet. These pieces, these massive plates, are what we now call tectonic plates. The story of their formation is a story of fire and ice, of heat and cold, of solidifying and cracking. It's a story that's been unfolding for billions of years and will continue to unfold for billions more. It's the story of our Earth, a story written in the language of tectonic plates. Beneath these plates, the magma is still moving, causing our tectonic plates to do the same. Now you might be wondering, how does this movement occur and what does it result in? Let's dive deeper into this fascinating phenomenon. At the heart of it all, the Earth's inner heat is the driving force. This heat, generated from the decay of radioactive elements and residual heat from the planet's formation, causes the magma to churn and move in a process known as convection. Picture a pot of soup on a stove. As the soup heats, it rises to the top, cools down, and then sinks back down, creating a continuous cycle of motion. This is exactly what happens with the magma in the Earth's mantle. But what happens when this magma movement meets the solid tectonic plates? Well, it pushes and pulls them, causing them to move. Yes, these gigantic plates are like rafts floating on a sea of molten rock. And just as rafts on the ocean can drift apart, collide, or slide past each other, so can our tectonic plates. Let's talk about what happens when these plates drift apart. When two plates move away from each other, magma rises from the mantle to fill the gap, solidifying to form new crust. This process is happening right now in the Atlantic Ocean, where the North American plate and the Eurasian plate are moving apart. This is how new ocean floor is created, in a process known as seafloor spreading. But what about when plates crash together? This is where things get even more dramatic. When two plates collide, the denser one is forced down into the mantle in a process called subduction. The intense pressure and heat cause the subducted plate to melt, and sometimes this molten material rises through the crust, resulting in explosive volcanic eruptions. Lastly, when plates slide past each other, they don't do it smoothly. The edges of the plates can get stuck while the rest of the plate keeps moving. When the force becomes too great, the plate suddenly slips, releasing a huge amount of energy. This is what causes earthquakes.
The San Andreas Fault in California is a prime example of this type of plate boundary. So, you see, the movement of these massive tectonic plates floating on a sea of molten rock is responsible for some of the Earth's most dramatic and awe-inspiring events. Earthquakes that shake our cities, volcanoes that reshape landscapes, and even the creation of majestic mountain ranges like the Himalayas are all the result of tectonic plate movement. These moving tectonic plates are the unseen force behind some of Earth's most dramatic events. And even though we can't see them, we feel and see the effects of their movements every day. So remember, the next time you feel the ground beneath your feet, you're standing on a piece of Earth's ever-moving puzzle.
Next time you stand on the ground, take a moment to think about what's beneath your feet. It's not just dirt and rocks, it's a massive tectonic plate, one of the many pieces that make up the puzzle of our planet. Isn't it incredible to think that the very ground we walk on is part of a constantly moving, ever-changing jigsaw? Let's take a moment to recap the journey we've taken today. We've journeyed back in time to when our Earth was a super hot ball of molten magma. We've seen how this magma cooled down over time, forming a thin, solid shell around the Earth. The Earth, ever the restless planet, didn't stop there. It continued to spin and move, causing this thin shell to crack. These cracks, much like the cracks on dried mud, divided the shell into large pieces. These pieces, these fragments of the Earth's crust, are what we now know as tectonic plates. Each of these plates is massive, often as large as a whole continent or even larger. Picture the entirety of North America or Asia, and you'll get an idea of how grand these plates truly are. But these plates aren't static. They aren't just sitting idly. Underneath them, the magma is still moving and churning because of the Earth's heat. This movement propels our tectonic plates, causing them to drift apart, crash together, or slide past each other. This movement of the plates, this slow but constant drift, is a key player in shaping our world. It's the reason behind earthquakes, when two plates crash together or one slides under the other. It's the cause of volcanic eruptions, when magma finds its way to the surface through cracks in the plates. And it's the creator of mountains when two plates collide and push the land upwards. But it's not just about the dramatic events. The movement of these plates also shapes our continents, our oceans, and our world. Over millions of years, they've helped create the familiar map of the world we see today. So, next time you look at a map or stand on the ground, remember the tectonic plates. Remember the massive puzzle pieces that are constantly moving, constantly shaping our world. They remind us that our Earth is a living, breathing entity, always changing, always evolving. Our Earth always changing, always working on its own giant puzzle thanks to the incredible tectonic plates. And you and I, we're standing right on top of one of those puzzle pieces, taking part in the great dance of the plates, in the grand story of our ever-changing Earth.